Okay, so chapter one deals with numerical and graphical summaries of data. Um, when we have a large set of numbers, often the first thing we want to do is try to summarize those numbers in some way, either summarize them by using just a few key numbers or summarize them with some kind of picture. This video will focus on the numerical summaries of data, and then there'll be another video for the other part of chapter one, which is the graphical summaries of data. So we have what's referred to as measures of center or measures of central tendency. The most common of which you're probably familiar with, which is called the mean. And to find the mean, you simply add all the numbers together and divide by how many numbers there are. This sigma notation you should be familiar with from other math classes. Notice like in a calculus class, there would probably be an index of summation above and below this sigma sign, but usually in stats classes in the formulas, it's just sigma of x subscript I or something like that. Also notice that there's the formula is the same. Add up all the numbers and divide by how many there are. Add up all the numbers and divide by how many there are. But there's different notation depending on if we're talking about the mean of a sample or the mean of a population. Sample mean is the symbol x bar, and population mean is the symbol mu. That'll be a bigger deal later on in the class when we have instances that we're referring to both the sample mean and the population mean, and we need those two different notations to keep that straight. So here's just a simple example. If I have this set of 8 numbers, which I'm going to refer to over and over again in these lecture notes, just add all the numbers together, divide by 8, divide by the number of numbers, and you get the mean, which is 18. To find the median is the number that's actually located in the center of our data. So to find the median, we need to put the numbers in order if they're not already presented to us in order. And if there's an even number of numbers like we have in this data set here, if there's an even number of numbers, then the median is actually going to land in between two of those numbers because we have 4 numbers in the lower half of data, and then we have another 4 numbers in the upper half of data. So the median is actually going to land in between the 4th and 5th number, which is the 14 and the 16. So the number that's exactly in between 14 and 16 is, of course, 15. If the numbers were a little bit trickier, the way you figure out that 15 is exactly in between those is to add them together and divide by 2. Our book has a special symbol for median, which looks like X tilde. If we have a data set with an odd number of numbers, then the median is actually one of those numbers. It's the number in the middle. Notice if we have 9 numbers, we have 4 numbers in the lower half, and then we have 4 numbers in the upper half, and this one number in the middle, 92. So sometimes the median is an actual number in the data set, and sometimes it lands in between 2 numbers of the data set. Okay, so measures of spread or variability. We often like to have a number that summarizes how far spread out the data is. The simplest one that a lot of students learn in elementary school is called the range, which is simply the maximum minus the minimum. So in our simple example here, the range would be 29. But there's 2 other measures of spread that get used in upper division classes much more than the range, and that's IQR especially, and also the fourth spread. The problem is that in order to talk about the IQR, which is interquartile range, we first have to talk about the quartiles. And in order to talk about the fourths spread, we first have to talk about the fourths. So the quartiles are locations within the data set that split the data into 4 pieces. we have 8 numbers in our data set. It's easy to split that into 4 pieces, but when you have a different number of numbers like 9, it's kind of impossible to split 9 into 4 pieces, but as close as we can get to splitting into 4 pieces, that's what the quartiles do. So once the median has divided the data into 2 pieces like this, then each of those pieces you just divide into 2 pieces. In other words, you find the median of the lower half and the median of the upper half. So these 4 numbers are the lower half of data. The middle of that would be right here, which is 11.5. And these 4 numbers are the upper half of data. The middle of that would be in between the 19 and the 23, which is 21. So these quartiles are referred to as quartile 1 and quartile 3, and sometimes referred to as the lower quartile and the upper quartile. And now that we know a little bit about the quartiles, that leads us to something the statisticians refer to as the 5-number summary. This is spit out and displayed by many software packages. The minimum, quartile 1, the median, quartile 3, and the maximum. And those 5 numbers are referred to as the 5-number summary. A lot of times I get asked, why do we have quartile 1 and quartile 3 and not quartile 2? Well, the answer is all 5 of these numbers used to be referred to as quartiles, quartile 0 through quartile 4. So the median used to be called quartile 2. And in some older textbooks, it's still referred to as quartile 2. So once you've determined where the quartiles are, then you can figure out the interquartile range, which is simply quartile 3 minus quartile 1. A pretty pain-free subtraction problem. So the interquartile range, or IQR, for our set of data is 9.5. By the way, if we had an odd number of numbers, like that set of 9 numbers that I showed you earlier, the median would not be included in either the lower half or the upper half. So we had the median, which is 92. There's 4 numbers below that, which get cut in half to find quartile 1. And there's 4 numbers above that, which get cut in half to find quartile 3. And whether we have an odd number of numbers or an even number of numbers, this way of determining the quartiles is exactly the same way that most of your graphing calculators do this. Our book, however, uses the terminology fourths instead of quartiles. And the fourths, the lower fourth and the upper fourth, as opposed to the lower quartile and the upper quartile, they're exactly the same as the quartiles if there's an even number of numbers. And the spread, either way, the fourth spread is exactly the same as the IQR, the upper fourth minus the lower fourth, just like we had before, quartile 3 minus quartile 1. The main difference between fourths and quartiles is when you have an odd number of numbers. When you have an odd number of numbers, you figure out the fourths by including the median in both the lower half and the upper half. So here's our 9 numbers, and we've identified the median as 92. If you count that 92 as part of the bottom half, then we now see that 53 is the middle of the bottom half, so that's the lower fourth. And then if you turn around and also include 92 in the upper half, the middle of the upper half lands on 107. And I'm kind of hammering this point home because some people are already familiar with using a graphing calculator to find the quartiles, but our book uses the terminology fourths, which are not always the same as the quartiles. By the way, if we use something like Microsoft Excel, here's these same 9 numbers in Microsoft Excel. Microsoft Excel gives us 2 different ways of determining the quartiles. So you see this one here, the 53. this one here, the 53, and this one here, the 107, those match up exactly with what our book calls the fourths, but the 51 and the 110 matches up with what we found earlier for the quartiles. So Excel gives us a way to do it either way. And then some books teach even more complicated ways of figuring out the quartiles that I don't really want to get into. It's just kind of unfortunate that there's not a universally agreed upon way to do this. But your book is going to talk about the fourths, so we have to know how to do it that way. So another way to measure spread is by using a measure called the standard deviation, which is a little bit more tricky to calculate. We're trying to figure out on average how far is the data away from the mean, or you could say how far does the data deviate from the mean, which is why we have the term standard deviation. So I've lined up the numbers in our data set, the 8 numbers in this column here. And the first thing I'm doing is I'm figuring out how far each of those numbers is away from the mean of 18. So I'm doing each x subscript I, each number in our data set, minus the mean. And I'm getting these numbers here. These numbers here are referred to as the deviations from the mean. Interesting note that the sum of the deviations from the mean is always 0. So if you combine these numbers, -8, -7, -6, and so on, that will always add up to 0. So you can't find the average distance from the mean by adding up the deviations from the mean, because the deviations from the mean will always add up to 0. So the most common thing that's done is to make them not add up to 0 is to square them all. So this next column I have is the squared deviations from the mean. And we're going to sum all of those squares. And that gives us a sum of 636. And then we're going to divide by n, the number of numbers in our data set. And that'll give us the average squared deviation of 79.5. This number is known as the variance. And variance is probably used more than standard deviation in some statistics classes. So it's kind of important to know the variance, and everything that we just did, we're going to wrap up in a little formula. Population variance, the symbol for which is the Greek letter sigma, that's lowercase sigma squared. The sum of the squares of the deviations from the mean divided by n. That's the population variance. And there's a little twist on this formula that, for whatever reason, mathematically works out to be exactly the same. Instead of doing the sum of the squares of how far all the numbers are from the mean, you can just do the sum of the squares of our individual numbers, and then do the sum of the numbers squared divided by n, and we'll end up in the exact same place. So the sum of the squares of the numbers in our data set would be 10 squared plus 11 squared and so on. The sum of our numbers, we saw that earlier, was 144 when we were figuring out the mean. So the sum of the numbers squared divided by n, and then this whole mess divided by n. So the sum of the squares of our data is 3228, and the sum of our data squared divided by n is 2592. Subtract those two and you get 636, which, surprise, surprise, is the same 636 we had up here, giving us the same answer for variance that we had down here. This second formula, sometimes called the computational formula or the shortcut, and that's included in many statistical software packages. I'm sorry, This is sometimes called the computational formula or the shortcut, and most statistical software will display both the sum of the x's and the sum of the x squareds. I wanted to go back up here and show you real quick on the calculator. If I put the numbers in our data set into the calculator, 10, 11, 12, 14, 16, 19, 23, and 39, and I asked the calculator to do some number crunching, which is stat calculate one variable statistics on list 1. Notice it gives me that the sum of the x's is 144, and it gives me that the sum of the x squared is 3228, which is that same 3228 that we had right here. Okay, so usually we don't have to do these calculations by hand because we usually have some kind of technology available to assist us. Then to find the standard deviation, all we have to do is take the square root of the variance. So the sigma squared now is just a sigma for standard deviation. And then this formula is exactly the same as what we had before, but all wrapped up in a square root sign. Or the computational formula all wrapped up in a square root sign. So 79.5 was the variance. The square root of 79.5 is the standard deviation. And the square root of 79.5 turns out to be 8.916. And if I go back to the calculator, you'll see sigma is 8.916. Now, if we're talking about the sample instead of the population, then these formulas get modified in a couple ways. There's more differences with these formulas than there was with the formulas for mean. So for sample variance, what happens is, first of all, instead of sigma, we use the letter S. So it's no longer S squared, it's no longer sigma squared, it's S squared. Instead of mu for the mean, we have the symbol X bar for the mean. Instead of capital N for the population size, we have lowercase n for the sample size. And then the real oddity to most students is that in this overall denominator, instead of dividing by n, we divide by n minus 1. Maybe by the time we get to around chapter 9, I'll be able to explain why we need to divide by n minus 1. But all you have to know is, for right now, that that's the formula. So the main difference is up here, right here, instead of dividing by 8, we would divide by 9. And so that 636, I'm sorry, right here, instead of dividing by 8, we would divide by 7. So that 636 divided by 7, instead of being 79.5, instead of being 79.5, is now 90.8. And then when we take the square root of that, again, the S squared is now S, and this formula for variance is wrapped up in a square root sign, and the square root of 90.8 is 9.53, and on our calculator, it'll also give us S of 9.53. A couple interesting points about variance and standard deviation. If you subtract a constant from every number in the data set, it doesn't change the spread, regardless of how we measure the spread. So for example, this data set we've been working with, the numbers 10 through 39. Suppose we subtract 10 from each number, giving us this new data set of 0 through 29. If I find the mean, of course, I'm going to get a different mean because I subtracted 10 from everything. And as a matter of fact, notice, surprise, surprise, the mean is now 8 instead of 18. The mean went down by 10 because I subtracted 10 from everything. But check out what happens with the variance. I'm going to use the formula where I sum the numbers squared, so the numbers in my data set squared and added together, minus the sum of my numbers, 64, squared and divided by 8, and then the whole thing divided by 7. So this 1148 number we hadn't seen before, and the 512 we hadn't seen before, but when we subtract those, we get 636 again, which is exactly the same numerator we had earlier, and 636 divided by 7 is 90.857, which is the exact same variance that we had just a couple lines up here. So subtracting 10 from every, or any constant from every number in the data set does not change the spread of the numbers. And this also applies to the spread measured by the IQR. So here's my new set of numbers after subtracting everything by 10. Notice that changes quartile 1 to 1.5. It changes quartile 3 to 11. But the IQR, subtracting the 11 and the 1.5, the IQR is still 9.5, just like it was before. So the IQR, as a measure of spread, does not change. Also notice the range, which would be the maximum 29 minus the minimum 0, the range is still 29 like it was before. Now, if you multiply every number in a data set by a constant, all of our measures that we've talked about, mean, median, quartiles, IQR, range, standard deviation, they all get multiplied by that constant, except the variance. The variance would get multiplied by that constant squared. So for example, I think I have these numbers in Excel somewhere. So here's these numbers in Excel. There's our standard deviation, and here is our variance of 79.5. If I take all of these numbers and multiply by 10, and then copy my standard deviation formula and copy my variance formula, notice multiplying all the numbers by 10 multiplied the standard deviation by 10, but it multiplied the variance by 100 because the variance is the standard deviation squared. Okay. Now, the last thing we need to talk about is outliers and extreme outliers. Sometimes a number or several numbers in a data set are very unusual. For example, this number 39 in our data set may seem unusually large. So there's a term for that in statistics. We call such a number an outlier, but there's a criteria that has to be met in order to call a number an outlier. So we start by calculating two outlier fences. And we do quartile 1 minus 1.5 times the IQR, and then quartile 3 plus 1.5 times the IQR. Any number less than the lower fence is considered an outlier, and any number greater than the upper fence is considered an outlier. Recall that for our data set that we had the numbers 10 through 39, this was our 5-number summary, and we had this for the IQR. So quartile 1 minus 1.5 times the IQR takes us to negative 2.75. Quartile 3 plus 1.5 times the IQR takes us to 35.25. We have no data that's less than negative 2.75, but we do have one number that's greater than 35.25, which is our maximum 39. So we say that 39 is an outlier because 39 is greater than 35.25. By the way, the fences are calculated in the exact same way using the fourths and the fourths spread. But of course, as we talked about earlier, sometimes the fourths turn out to be different numbers than the quartiles if you have an odd number of numbers. But with the fourths, the lower fence is lower fourth minus 1.5 times the fourth spread, and the upper fourth, upper fence is upper fourth plus 1.5 times the fourth spread. And there's another category of unusualness referred to as extreme outliers. And the determination is exactly the same as what we just went over, except we're going to multiply the IQR, or the fourth spread, by 3 rather than 1.5. So that would look something like this. Quartile 1 minus 3 times the IQR, quartile 3 plus 3 times the IQR. So if we do that for our data set, we get a lower fence of -17 and an upper fence of 51.5. And we have no data that's less than -17 or greater than 51.5. So none of our data would be considered an extreme outlier, and only the 39 is considered a regular outlier. So that should get you through a good chunk of the Chapter 1 homework, and be watching for another video on the different graphical summaries of data.